Welcome to Learning Unit 2. This video will cover concepts of networking, traditional versus IoT networks, and various IoT architectures, including peer-to-peer, edge-based, and cloud-based, along with performance evaluation, security, and interoperability. The peer-to-peer or P2P IoT architecture enables devices to share resources and communicate directly, minimizing the load on central servers. This one-to-one communication is particularly efficient for large-scale deployments. In this architecture, various IoT devices, such as laptops, smartwatches, smartphones, and even homes, operate as peers, communicating directly with each other in a decentralized network. In P2P IoT, devices communicate directly without central servers. Participants include IoT devices, optional gateways, and peers. The flow involves device A detecting an event and sending data directly to device B, which executes the action without cloud interference. Real-world P2P examples include smart homes, where sensors trigger lights directly. Industrial IoT uses P2P for safety shutdowns. Connected vehicles use V2V communication to avoid collisions. Drones and sensors form ad hoc P2P networks for disaster response when the cloud is unavailable. Here are some real-world examples. Smart homes, industrial IoT for safety shutdowns, connected vehicles using V2V communication, and disaster response utilizing ad hoc P2P networks. P2P offers very high responsiveness and strong fault tolerance. However, stability can be an issue if peers frequently drop out. Scalability is complex for very large deployments, and security is mixed, as enforcement is harder in a decentralized setup. Direct device-to-device, D2D, communication in IoT is foundational for low latency and autonomous coordination, enabling devices to exchange data or commands without cloud intermediaries. This graphic illustrates direct peer-to-peer communication between different IoT devices. Advantages of D2D include ultra-low latency, resilience without internet, data privacy, and energy efficiency. Limitations involve range constraints, complexity in device discovery, security risks in authentication, and challenges in scaling large dynamic networks. D2D participants include IoT devices and protocols like Bluetooth, Zigbee, and Wi-Fi Direct. The flow is direct. Device A sends a signal to device B, which responds without cloud involvement. Examples include smart home automation, industrial safety coordination, and V2V communication. The evaluation criteria for D2D communication show ultra-low latency and very high responsiveness. Fault tolerance is strong, stability is moderate, and scalability is limited. Resource efficiency is high, and interoperability is good with standardized protocols. D2D communication is best suited for domains requiring local automation, such as smart homes, industrial automation for safety-critical coordination, connected vehicles for V2V alerts, and disaster management. Blockchain-based P2P IoT architecture combines decentralized peer-to-peer communication with distributed ledger technology. Devices communicate directly, while the blockchain layer provides trust, transparency, and data immutability for all transactions and exchanges. The architecture involves peer-to-peer communication between IoT devices, where transactions are recorded on a blockchain ledger. Consensus mechanisms and smart contracts ensure reliable data exchange and automated actions. This diagram illustrates the blockchain process. A transaction is requested, a block is created, sent to all nodes for validation, and once consensus is reached, the block is added to the chain and the transaction is complete. Key participants include IoT devices generating data, peers or nodes validating and recording transactions, and a consensus mechanism ensuring agreement. Smart contracts automate actions when predefined conditions are met in the system. Blockchain-based P2P architecture has real-world applications in smart homes for transparent energy billing, industrial IoT for tamper-proof maintenance logs, and healthcare for securing patient vitals and audit trails. Advantages include enhanced trust, transparency through an immutable ledger, decentralization eliminating single points of failure, robust security, and automation via smart contracts. Limitations include potential latency from consensus, resource constraints on IoT devices, scalability challenges, and system complexity. Evaluation criteria show moderate to high latency, depending on the consensus mechanism. Fault tolerance, stability, security, and privacy are very strong due to the distributed ledger and encryption. Scalability and resource efficiency remain challenging. This architecture is ideal for domains requiring high trust and transparency, such as energy billing in smart homes, secure maintenance logs in industrial automation, immutable patient records in healthcare, and transparent governance in smart cities. Mesh networking, exemplified by Thread and Zigbee, is the physical realization of P2P. Devices relay data through each other, instead of relying on a central router. This provides resilience, scalability, and extended coverage, making it crucial for connecting large numbers of devices. The core concept of mesh networking is that every device helps relay data, similar to a bucket brigade. This creates a highly resilient network structure, where data automatically reroutes if a node failed. Zigbee is based on the IEEE 802.15.4 standard, offering self-healing capabilities and defining specific device roles, coordinator, routers, and low-power end devices. Thread is IP-based, IPv6, meaning every device has an IP address, and it uses a border router to connect to the wider internet. Thread is foundational to the Matter standard. This image illustrates the mesh networking topology, where multiple devices connect to each other, ensuring that if one path fails, data can be rerouted through another device. Key takeaways are that Zigbee is excellent for local, low-power networks, while Thread is future-proof, IP-native, and essential for cross-brand interoperability via Matter. Both enable scalable, self-healing IoT networks.